Picture this. You're paying for something on PhonePe or Google Pay, but your payment stuck. You hit that cancel button and then you get that message. If amount is debited, it will be refunded within 3 or 5 working days. Now imagine you're the engineer who built that payment system. You have two choices: Thread.stop and pray, or tell your boss why that's a terrible idea. Here is the thing that Java never tells you: there is no safe way to preemptively stop a thread. Zero, none. The methods that claim to do it, they are all deprecated for a reason. Today, we are going deep into task cancellation and executor shutdown. By the end, you'll know exactly how to stop tasks safely, why interruption is your best friend, and how to build systems that shut down gracefully even when things go wrong. Hey everyone, welcome back. If you are new here, we break down complex concurrency concepts into stuff you can actually use at work. Today's topic is one of the most misunderstood parts of Java. We are talking about cancellation and shutdown. Why do threads need to stop? Well, lots of reasons. Maybe a user clicked cancel on a long operation. Maybe you are searching for something and you only have 2 seconds to find the best answer. That is timed processing of task. Or maybe one task found the solution so everyone else should stop. Or maybe the whole application is shutting down and you need to clean up nicely. And here is the scary part: if you do this wrong, you can leave shared data in a broken state, leak resources, or prevent the JVM from exiting altogether. So, we'll cover today why Thread.stop is pure evil and what Java offers instead. Then, the cooperative approach using flags and interruption, how Future.cancel makes life easier, building services that owns threads, and how to shut down them properly, what to do when threads die unexpectedly, and a bonus tip on demon threads that might save you someday. This is the stuff that separates junior devs from engineers who get paid the big bucks. So let's dive in. Let's start with the question: why doesn't Java just give us a method that instantly stops a thread? Wouldn't that be easier? Well, Java actually had those methods: thread.stop, thread.suspend, thread.resume. They are all deprecated, and there is a good reason for that. Imagine you're writing data to a file, you open it, you write half the content, and then bam, someone calls thread.stop on your thread. What happens to that file? It's corrupted, half written. The locks you were holding never released, or the threads are now stuck forever waiting for those locks. It's like someone yanking the steering wheel out of your hands while you are driving. Pure chaos. The Java designers realized this was a disaster, so they removed the ability to force stop threads. Instead, they gave us something better: a cooperative mechanism called interruption. Here is the philosophy: Only the thread itself knows when it's safe to stop. So instead of forcing it, we politely ask, we say, hey, whenever you are at a good stopping point, would you mind wrapping up and exiting? That's what interruption is, a request. I repeat, a request, not a command. So, how do we make this request? And more importantly, how do we write a code that listens? Let's start with a simplest approach, a cancellation flag. Let me show you a basic example. Imagine we have a task that generates prime numbers and we want to be able to stop it. Here is a naive but working approach. Look at this task prime generator, which implements runnable interface. We have a cancelled flag here, which is marked volatile. In the run method, we check that flag in a while loop. As long as it's false, we keep generating the primes. When someone calls cancel method, the flag becomes true and the loop exits on the next iteration. Simple, right? And it works most of the time. Here is how we would use it. We start the generator, let it run for a second, then we cancel it from a finally block. This ensures cancellation even if something interrupts our sleep. But there is hidden problem here. What if the task is blocked? What if it's waiting for something like a space in a queue? It might never check the flag. Let's look at a broken version. Same idea, but now we are using a blocking queue. The producer generates prime and puts them into a queue. The consumer reads from the queue, everything is fine until producer gets ahead. When queue fills up, queue.put blocks. So our producer thread waits and waits and waits. Now imagine the consumer decides it had enough. It calls cancel method which sets the flag to true, but the producer is stuck in put method. It never checks the flag. It never wakes up. The cancellation request just vanishes. This is the problem with plain Boolean flags. They don't help when the thread is blocked. But wait, if interruption can wake up a blocked thread, does that mean it's dangerous too? Can it interrupt critical operations at a wrong time? That's a great question. Stick around. Let me introduce you to interruption. Every thread has a Boolean flag called the interrupted status. It starts as false, and when you call interrupt method on a thread, you set that flag to true. But here is the key. Setting the flag doesn't stop the thread. It just sends a signal. The thread has to check the signal and decide what to do. There are two ways to check. First is interrupted method. This just reads the flag, leaving it unchanged. And the second is interrupted. This reads the flag and clears it. So use it with caution. Now, when our consumer calls cancel method, which just calls interrupt method, two things happen here. First, if the thread is blocked in put method, that method throws interrupted exception immediately. And second, even if it's not blocked, the next loop iteration sees the flag and exits. Beautiful, right? But notice, we catch interrupted exception here and just let the thread exit. We are swallowing the interruption because we know the thread is about to die. That's okay here. But in most code, you need to be more careful. Here is where things get subtle. Remember how I said interruption is just a request? Well, different code has different responsibilities. Think of it like house sitting. If you are watching someone's house, you don't throw away their mails or packages. You save it for when they return. The same applies to threads. When you write a task that runs in a thread pool, you don't own that thread. The thread pool owns it. Correct? So if you catch an interrupted exception, you shouldn't just swallow it. You should either rethrow it, meaning propagate it, if your method allows it, or restore it by calling this method interrupt, which restores the interrupted status. The only time you can safely swallow an interrupt is when you own the thread and you know it's about to die, like our prime producer example. Otherwise, always pass the signal up. Now, what if you are using an executor service and you submit tasks? Surely there is an easier way to cancel them, right? Yes, and that is called future. When you submit a task to an executor, you get future. That future has cancel method, which takes a boolean may interrupt if running. If you pass true, it will interrupt the thread running the task. But if you pass false, it just says don't start it if it hasn't started yet. So look at this beautiful pattern. We submit a task, then we call future.get with timeout. If it times out, we catch timeout exception. And finally, we cancel the task with true. This ensures the task is interrupted if it is still running. This is how you build time limited operations in production. No manual flag checking, no complex coordination, just future.cancel, and you are done. Now let's talk about something bigger. What if you have a service that owns its threads, like a logging service that writes messages asynchronously? This looks clean. A background thread takes messages from a queue and writes them. Multiple producers call log method to add messages. But how do we shut it down? If we just interrupt the logger thread, what happens to the messages still in the queue? They are lost. And worse, the producers blocked on a full queue will stay blocked forever. We need a real shutdown policy. So here we have an improved log service with reservations counter. We have a thread sep queue that blocks producers if it is full and blocks consumers if it is empty. We have created a dedicated consumer thread, a logger thread instance that will continuously take messages from the queue and print them. Here we have a flag to indicate whether the logging service is shutting down. It prevents new messages from being accepted once shutdown begins. Then we have a reservations counter. This tracks how many messages have been reserved, that is, promised to be logged, and it is incremented when a producer adds a message, and it gets decremented when the consumer finishes logging it. This ensures shutdown waits until all pending messages are processed. Then the start method. It starts the logger thread. Without calling this, the consumer won't run and messages will pile up in the queue. Now let's go to the logger thread, but before that, let's check this log method. So this method is called by producers to add a message. Inside synchronized block, it checks if shutdown has started, and if yes, it throws an exception, which means no new logs allowed. Otherwise, it increments the reservations, a promise that one more message must be processed. Queue.put message adds a message to the queue and it blocks if necessary until space is available. Let's take a look at logger thread. This is the entry point for the thread's work when we call start method. It logs on the outer log service instance. That's why it's log service.this to safely check the shared states. If service is shutting down and there are no pending reservations, the loop exits. This ensures the thread only stops once all queued messages are processed. If shutdown conditions are not met, then it attempts to take message from the blocking queue. The queue.take method will block if queue is empty, waiting until a producer adds a message. After retrieving a message, it decrements the reservations counter. This is actual logging action in simplified implementation. If thread is interrupted while waiting on queue.take method, it catches this interrupted exception. Instead of exiting immediately, it continues to next loop iteration where it rechecks the shutdown condition. This allows graceful shutdown rather than abrupt termination. And when we end the loop and enters finally block, the finally block is guaranteed to run whether the loop exits normally or due to an exception. This is the right place to close the resources, for example, file handles, network connections, if you extend the logger later. Now let's go back to the stop method. So this, when we call this method, it marks the service as shutting down. The synchronized block ensures thread sep update of this each shutdown flag. Logger thread.interrupt method wakes up the consumer if it is blocked on queue.tick, so it can recheck the shutdown condition once it performs the next iteration. That's why we don't exit this loop immediately. So that's the solution which ensures when shutdown is called, we set the flag and interrupt the consumer. The consumer keeps running until the queue is empty and reservations hit zero. Only then it exits. So all pending messages are written and no producer gets stuck. Executor service gives us two shutdown methods. Shutdown, which is graceful, it stops accepting new tasks but lets existing tasks finish. And shutdown now, which is abrupt, it tries to cancel all running tasks and returns a list of tasks that never started. Which one should you use? It depends on your safety requirements. If you are processing payments, you probably want shutdown. Let those transactions complete. If you are doing experimental calculations and the user just wants to stop, shutdown now might be fine. But here is the problem with shutdown now method. You don't know which tasks actually completed. Some might have been interrupted mid execution. If you need to know what was left undone, you have to track it yourself. Look at this clever tracking executor. It wraps a real executor and remembers which tasks were cancelled mid execution during shutdown. The task cancelled at shutdown, it is a thread set that stores tasks that were cancelled when the executor shut down. Get cancelled task method, it returns a list of tasks that were cancelled due to shutdown. When we call this method, if the executor isn't fully terminated yet, it throws an exception. This prevents reading incomplete data, and at last, it wraps the set into a new array list to avoid exposing our internal mutable state. Then the execute method, it wraps the submitted runnable inside another runnable, which is a lambda. The try finally block ensures tracking logic runs even if the task throws an exception. So inside this finally block, we check if the executor is shutting down and the current thread was interrupted, which usually happens when the tasks are cancelled during shutdown. If both conditions are true, then we add the task to tasks cancelled at shutdown set. After shutdown, you can call getCancelled method to see what didn't finish, and based on your business requirement, if it is allowed, you can reprocess them. Can you guess where something like this actually be used in the real world? Surprisingly, this is exactly how web crawlers save their state. When shutdown happens, they record which pages were still being crawled so they can resume later without starting from scratch. There is another way to shut down producer consumer systems, the poison pill. It's a special object you put in the queue that means stop. When the consumer sees it, it knows there is no more work coming. It finishes any remaining items and exits. So here we have a constant string poison. This acts as a special marker message to signal the consumer thread to stop gracefully. With start method, we start both threads, producer and consumer. Start method for each thread internally calls a run method asynchronously, and when we stop the producer thread, it's interrupted, requesting a producer thread to stop. Then we call join method on the producer thread to wait until the producer thread finishes execution. Then we put poison pill in the queue so the consumer knows it should stop, and then we wait until consumer thread finishes the execution. So if we take a look at producer thread, so when we interrupt producer thread, it catches the interrupted exception and exits gracefully. And in consumer thread, when it consumes poison pill, it breaks the loop and stops. This works great when you know exactly how many producers and consumers you have. If you have multiple consumers, you need multiple pills, one for each. If you have multiple producers, each producer puts a pill. Poison pills are simple and reliable, but they only work with unbounded queues. If your queue has limit, the pill might never get in. Now, can you tell me what happens when a thread dies because of an uncaught exception? This is more common than you think. Runtime exceptions, null pointers, bugs, they can take down a thread instantly. If that thread was essential, like if it was a worker thread in a pool, the pool might replace it, but you lose the task that was running. Java gives us a way to catch such exceptions. Uncaught exception handler. Here is a simple handler that logs the error. Now, when thread dies unexpectedly, you at least know why. So, how can you use this? So, you can attach this per thread using this setter. You can keep this as a default for all threads by calling the setter method on thread class. And if you have to set this for threads inside executor pool, you can create a factory for a thread, and for each thread you can set this uncaught exception handler and pass that factory as method arguments to your pool. But note, this only works for tasks submitted with execute method. If you use submit method from executor framework, exceptions are captured in the future and you only see them when you call get method on that future. One last concept, daemon threads. This is a flag which represents whether or not the thread is daemon thread. These threads with daemon flag equal to true are background threads that don't prevent the JVM from exiting. When the daemon threads are only left, the JVM just stops without caring about these threads. No cleanup, no finally blocks, it's gone. This sounds useful but it's dangerous. If a daemon thread is writing to a file when the JVM exits, that file gets corrupted. If it is holding a database connection, that connection leaks. Daemon threads should only be used for housekeeping tasks where it is okay to lose work like cache cleanup, statistics collections, things like that. But it should not be used for IO or critical operations. Alright, before we wrap up, let's quickly recap what we covered today. First, we learned why you can't just force stop a thread. Java's answer is cooperative cancellation. The task decides when it's safe to stop. Second, we looked at two ways to request cancellation. The simple Boolean flag works for tasks that check it often but fails when the thread is blocked. That's where interruption comes in. It can make up blocked threads and give them a chance to exit cleanly. Third, we talked about interruption policies. If you don't own the thread, you should either propagate the interrupted exception or restore the interrupted status. Swallowing interrupts is only safe when you know the thread is about to die. Fourth, we saw how Future.cancel makes cancellation easy when using executors. One line of code can stop running tasks. We compared Shutdown versus shutdownNow, graceful versus abrupt termination, and we looked at how to track which tasks were cancelled using a custom executor. We covered poison pills, a simple but effective way to stop producer consumer system when you know the number of producers and consumers. We also learned about uncaught exception handler to catch unexpected thread deaths and log them. And finally, we touched on daemon threads. This was a long one, over 30 minutes of hardcore concurrency. If you made it this far, you are serious about becoming a better engineer. That's all for this video. I'll see you in the next one with a new problem. But until then, remember, be kind to your threads because they are doing their best. If you found this video helpful, please give it a thumbs up and subscribe for more technical content.